Okay, so for real data, what are the interesting projections? Um, so John Tukey had this idea back many, many years ago about looking at, not looking at all possible projections, but only looking at the most interesting ones and having a computer program or algorithm try to find the most interesting uh, views for us to look at. He called this cognostics. You can think of that as computer-aided diagnostics. We're looking for have the computer do most of the work to find the interesting projections. And John and Paul Tukey first suggested doing this for looking at scatterplots. So finding what are interesting scatterplots, doing a search over all possible pairs of scatterplots and find the most interesting pairs. And they call this thing scagnostics, for scatterplot cognostics, or sometimes scatterplot diagnostics. But we're looking for having some method of deciding on what are the interesting pairs of variates to look at, and could you show us only the most interesting? So the question, of course, becomes what is interesting? And there are a number of characteristics of a point configuration in a scatterplot that might be interesting. So here are a few that look like they could be of some interest. So in this first group, you may recognize this is two different clusters. That's an interesting scatterplot that the data separate in this way. Or perhaps here we're interested in things that are a skew distribution. So we've got a pile up along a concentration along the bottom here and spread out. Or we've got, a couple of outliers here, but really, for the most part, a monotonic relationship relating these two variates. And maybe this is not so much interesting, but we at least know that it's kind of a convex shape. Here's again a mostly linear shape that with a negative correlation. Again, in this here, there may be some little clusters here that might be of interest. Could we find that? Here, outlying points with a concentration that this data are kind of sparse. Clear concentration on lines here around the edges of this square, and perhaps some lines in the middle. Also lines here that we see appearing in this data that we'd like to be able to explain what are those lines. So we'd like to have the algorithm draw those things to our attention. Again, two quite different clusters here, and a lot of strange structure here on the bottom left corner. Again, with maybe sort of curves that appear there, but also this kind of cross-shaped structure that might be of interest. And again, grouping here, some monotonic relationship, again, roughly monotonic relationship, but also a little bit of non-convexity, lines here and sparsity. So lots of different things, and you can imagine very many more. What would be interesting? The question is, how do you capture that mathematically so that we can encode it? And if we can capture mathematically, can we actually compute it quickly enough that it's actually of some use? Because remember, we have to do this calculation over all pairs of variates if we're going to find the most interesting. It means we have to find some way of mathematically describing an interesting feature and then calculating that on all pairs, which, as we know, explodes, has a combinatorial explosion as the number of variates increases. So here's some examples. Well, we saw things like correlation, so we might be interested in, is there that kind of straight line relationship? So looking at a sample correlation, that's easy enough to calculate. Calculate that over all pairs xi, yi for all pairs of variates. Or we might have some notion that that the data line here, some small smooth area, so we might run a smooth over the whole scatter plot and think about how well are we fitting, how much of that smooth, how much of the variation in the data, the summation of yi squared, is that smooth explained. So this could be a calculation of the larger that is, the closer the data seem to lie to a smooth. Same with this correlation, the larger that is in absolute value, the closer the data are to a straight line. The other way we can look at, again, smoothing, there's maybe no reason to assume y is the response and x the explanatory, but rather the other way around. X is the response, y is the explanatory variate. Could calculate that in that direction. Maybe even if we're thinking about it in one direction or the other, we might calculate both of these and take the max over them. There are lots and lots and lots of possibilities. And we could apply any of these to transformations of the data. So, for example, an interesting transformation is taking the ranks. So if we took the ranks, took the correlation of the ranks, we'd be able to tell whether or not there's in fact a monotonically increasing or decreasing relationship between x and y without specifying necessarily that that might be linear. So correlation, the sample correlation on the ranks is effectively something called Spearman's rho, and that is good for telling whether it's a monotonic relationship or not. We might also look at things that are a little less statistical, thinking about the geometry itself. So this is an approach taken, as you'll see shortly, by Lee Wilkinson, Graham Wills, and others, other co-authors. And so this is the point configuration here. So we want to summarize how could we summarize this point configuration in a way that might be useful to then operate on that summary to see whether or not there's any interesting pattern. So summaries are nearest neighbor graphs, where we connect every point to its k nearest neighbors. In this graph here, we've got 3 nearest neighbors for that configuration. So that graph itself might be of interest, and maybe the features of that graph like the average, let's see, the average degree, or the length of the edges, or the radius of the graph, etc. Lots of different measures that you might imagine. Another graph would be the minimal spanning tree, and this is where every point is connected. And what we do is we have a connection connecting all the points here. It can't have any cycles, so not like this neighbor graph. There's no cycles in it. That is, it's a tree. It spans, so all points are connected, and it's minimal in the sense that the sum of the length of the edges on this tree is as small as possible. Okay, so that's the minimal spanning tree. Alternatively, we may just want to put a sort of rubber band around the outside of these points and say, what's that convex hull? So define that to be the convex hull and think about properties of the convex hull. You know, what's the area of it, what's the perimeter of it, etc. Same with the minimal spanning trees. We'll see, we're looking at, you know, what is the degree distribution, what's the radius of it, what do the angles look like that are formed by the edges in the minimal spanning tree. Lots of information here that we might be interested in using. So the classic, let's see, a graph here is also Delaunay triangulation, in which the convex hull is going to be a subgraph as is the minimal spanning tree. So we look at this Delaunay triangulation is a nice way to describe the relationship between all of the points there. So we have all these triangles between 3 points. Converse of that is a Voronoi diagram, sort of complementary to this, that helps define this. And this Delaunay triangulation now can be related to something called an alpha shape or an alpha hull. And principally what we're looking at is, can we bring in circles here that will cut through this of a certain radius without hitting any neighboring points. And if we can, we get to cut away these edges. And so what we're looking for is some measure of cutting away the edges from the convex hull to show when the data is really supporting an indentation there. So this is kind of a measure of not the rubber band around the outside of the whole thing, but rather getting closer to the covering all of the points without adding too much extra information. So, and that is all going to depend upon a particular parameter alpha. So there are lots of different alpha hulls depending on the choice of a tuning constant. But now we might think about, for example, how convex this data might be measured by thinking about the area of the alpha hull divided by the area of the convex hull. That is, if the alpha hull is very nearly the convex hull, then the data look kind of convex. If the alpha hull is much smaller than the convex hull, then it's perhaps not a convex data set. So we use these kind of structures to try and capture the geometric structure of the data and hopefully have some simple measures based on this structure that will provide us with interesting scatter plots. So here's some examples. So this one I just mentioned, thinking about some kind of measure of the convexity. So I can think about the area of the alpha hull divided by the area of the convex hull. The closer that is to 1, the alpha hull area is always smaller than the convex hull. So the closer that is to 1, the more convex the data appear to be. We could also think about how skinny is this thing. So, skinny that's a word that's being used here. This particular calculation captures some things that we mean by skinny, not other things. But I'm not going to go into that. I'm just going to call this skinny. And the idea is comparing the area of the alpha hull to the perimeter. Right. So if this area is really big, related to the perimeter, right, then this is going to be close to 0, and it's not going to be very skinny. And so this is a funny choice here. And the choice is, if you imagine the area of A is actually a circle, you've got 4 pi times pi r squared. So you've got 4 pi squared r squared. So the square root of that is 2 pi r, and that would just be the circumference of a circle. So that would be 1. So the notion is that a circle is the least skinny. It's going to get us down to 0. And otherwise, if this is this area is much larger than the perimeter, then if the area is much smaller than the perimeter, then it's going to be a skinny shape. So trying to get that kind of idea across. So other possibilities, looking from the spanning tree. If you think about V being the number of vertices and VK being the number of vertices that have K edges in the minimal spanning tree, they have degree K. Then we might think about what is stringy. Well, stringy, the configuration might be stringy if there are lots and lots of vertices that just have 2 edges. Okay, so each point doesn't connect to a whole bunch of other points there, but they actually connect. There are a lot of points that just connect to 2 others. So a measure of the number 2 degree vertices, excluding the ones that have 1 degree, as a proportion might be a measure of how stringy it is. The larger this is, the stringier the data seem to be. We might look for lines. This is called striation, looking for lines in the scatter plot. And we could do that again looking back at this minimal spanning tree. So again, stringy if there's lots of these 2 degree things, and not so stringy if there aren't so many, large proportion of those. And look for lines. Well, if the angle formed here between every pair of edges that are on a vertex of degree 2, if that angle is near 180 degrees, then this is close to a line. And so if we look at the angles formed here and have some summary of that, we might think about using that summary to talk about how many lines there are, or the fact that there are many lines in the data set. They don't care about the orientation, it's just the degree of the angle made by the 2 degree nodes. So lots of things that you can imagine, and Wilkinson, Wills, and others, and Grossman have built in scagnostics based on these geometric measures. So they propose actually 9 scagnostic measures, and they have these various names: monotonic, skinny, stringy, and we've talked about some of these. Monotonic is that thing measuring Spearman's rho. Stringy, we've talked about. Skinny, we've talked about. And here are some data configurations that they have, which are related close to the value that that scagnostic has. So again, we've got extremes: extremely non-monotonic, extremely monotonic, extremely not stringy, very stringy, not skinny, very skinny. So they're trying to capture these things, and these are in the middle values. All these scagnostics are scaled to be between 0 and 1, with 1 being that's the high values of that, and 0 the low, or where that feature is least present. So convex on the right, there's a very convex data set. On the left, very non-convex. Right, there's this big gap here. You can imagine what the alpha hull looks like compared to the triangle that forms the convex hull. Striated, not too many lines here, more lines there, lots of lines here. Most of the data are in lines. So on the minimal spanning tree, so the minimal spanning tree is going to go there and connect across here somewhere, down here and connect across there, probably up here somewhere. Okay, one of these nearest points. So again, striated, we're looking at the number of roughly what proportion or what's the average angle between 2-degree nodes, and you can see a lot of them are very near 180 here. Sparse, trying to capture whether there's lots of space between the points. So we have things here where there are very few different values that are highly sparse, and these are not sparse. Clumpy, looking for groups, again based on this thing called runt pruning, and it's which in turn is based on the minimal spanning tree. And skewed, this is looking at the distribution. Is the distribution of the interpoint distances on the minimal spanning tree, is that a skewed? How skewed is that distribution? It's debatable whether that actually picks up anything interesting. Looks like high and low skewed values are also very interesting. The middling skewed and maybe not so interesting. And outline, whether there are outliers in the data. So those are 9 scagnostics measures, and of course they're not completely independent. So Wilkinson et al. Sort of also provide this chart, where in the top row we've got all of these different possible scatter plots, and in each column then we have the measures outlined through monotonic, where high values of, so for this particular scatter plot here, second from the right, it has high values of outlying and skewedness, and low values of clumpiness and monotonicity and stringiness. And conversely, over here on this sort of spring-like curve through here, the sinusoidal curve, we have low values of outlying, skewedness, clumpiness, convexity, higher value on skinny, very high values on striated and stringy. So you get some idea that some of these plots are going to trigger several scagnostics, and some are not, or perhaps only going to trigger one. So this curve here is definitely looking like it's skinny is the big trigger that it has, etc. So they kind of make sense looking at these pictures, what they trigger. You can imagine why they trigger these different measures. So perhaps these measures are getting close to capturing what their names suggest. Okay. So in R, there's a package based on the Wilkinson et al. Code in Java. This R package implemented by Simon Urbanak, and we'll just get the scagnostics. So you have this the data set here. We have all the olive acids. Take the scagnostics of it, and it returns. I've got the transpose here, just showing you the first few rows. For every pair of variates, so that's a pair of variates, that's a pair of variates, we have the corresponding scagnostic measure. It's outlyingness measure, its skewedness measure, its clumpiness measure, so that's very highly skewed, but low on clumpiness, and low on sparsity, higher on monotonicity, etc. So you have all of the data calculated, all of these scagnostics are calculated for all pairs of variates in the data set that you give it. So you've got 9 measures. So no matter how many variates we had in the data set, we reduce that to 9 variates, because we're going to look at what are interesting pairs of variates here. Okay, so we can have scagnostics work together with our other displays. In this case, looking at the temporally linked things, the navigation graphs. So we can use those to decide perhaps which nodes. Every node in a navigation graph is a pair of variates. So maybe we should only have those pairs of variates which have high values of the scagnostics, which are of interest to us, and not have the other ones. And that allows us to explore particular subspaces that have the features that we may be looking for, might be of interest. So what I can do now is looking at the olive data itself. So I'm just going to calculate that. And in Loon, there are a number of things that are useful for looking at these measures of interest on scatter plots. So this is L_NG for navigation graph ranges. We'll just have a look at what that looks like. So when you execute that code, you're going to get this navigation graph, this scatter plot. There's the inspectors before, and you notice that this navigation graph is now not all 8 choose 2 pairs of variates, but only 4 variates. And it's looking at particular measures here, monotonicity, and this is a 3D transition graph. And the values of the scagnostic for monotonicity are between 0.6 and 0.76. So these 4 pairs of variates have scagnostics measure of monotonicity somewhere in there. That's measure of Spearman's row. So if I were to look around here and the scatter plot, just navigate through that, you see there is a monotonic relationship between here, and as I move around, in fact, I'm picking off these definitely the most monotonic scatter plots underneath, and back to the source. So it's picking up the monotonicity. I might also look for convex, and now that's just between 0.47 and 0.537, so maybe I'll go for the percentile. So the top 20% of the 8 choose 2 pairs are here appearing there. That's going to be these 6 pairs of variates, and these are ones that have the highest value of convexity. And you can sort of explore that a little bit. Yeah, lots of convex stuff. Well, it turns out, I mean, convexity is usually not that interesting. So we could move this and just say I'm interested in the least convex. That's often a more interesting measure. So now I've got a different set. You can see that that's not a convex data set. So that measure that we suggested, looking at comparing the alpha hull to the convex hull, the areas, measure it. And look at that structure that's appearing. So these are the non-convex, and those are all kind of interesting structures to discover. Lots of structure in that data. Picked up. So non-convexity is often a choice that's of interest. You also see lines in there, so it shouldn't be at all surprising that many of those should also come together when we look at, say, striated. Okay, so striated, the top 20%, or just look at the values. Wow, that's clearly the one that has the most lines. It's only picking up one pair, and there you have, you can see these lines there and a horizontal line. Again, the top 20%, maybe the top 15%. So suggesting these are the pairs of variates that demonstrate the lines in the data. Oh yeah. Not always the same lines, are they? So in fact, between there and there, different groupings. So halfway there, you're seeing a bunch of different lines. And that's got to do with the granularity of the measurement that's in the olive data. Okay, so there's a nice coupling of and you could look at the 4D transition if you wanted, so we could change this to have both together, I guess. So we have the complete graph here, the lines. So LNG ranges allow you to look at one scagnostics at a time, and note that these are measures. They can be any kind of measure. We'll get to that in a minute when we're using the output of the scagnostics measures. So as before, we could add, link radial plots to see radial axis plots to the scatter plots, so that we can see all of the dimensions at once. And we'll just do this here for this. So let's see if I can find an interesting view here. Oops. Oh, there we go. Lined up. So what I'm interested in is that horizontal line there. So looking at this horizontal line seems to be going across versus these vertical lines are some of these guys that are in the vertical here, do they belong in vertical lines or do they belong in the horizontal? So you might think about how different are these horizontally versus vertically by just looking at the glyphs that are there. So the guys that are in vertical, like that one is rather different from everybody above here. This guy's different. And you might think about, can we distinguish? It's kind of hard to tell in some places. You can certainly see some of these glyphs that are quite different from the others in that vertical line. So they're different other variants, that one there, for example. Okay, let's pick them all and put them back. Maybe I think if I'm really looking at lines, I should look at the striated. Yeah, so that's a better view. Do these guys, how do they appear? That those vertical lines versus the horizontal. And again, look at the glyphs. So some of these that you'd imagine, some of these glyphs that do not look like the vertical grouping should perhaps be in the horizontal grouping. You might try to disambiguate these different lines. Ones that all go across this way should perhaps look a lot alike. As you can see, these guys look like these guys, look a bit like those guys, and those guys look rather different. So maybe this group here is part of that horizontal line as opposed to these ones that are part of the vertical line. So maybe we would distinguish those two groups that way. Okay, back to looking at all the data. So back to the slides. So we can have that work in conjunction with other displays that we've already spent some time exploring. Another interesting approach is rather than looking at one measure at a time, we can look at two measures at a time. So this is LNG plots. And we'll just execute this code and we'll see what you get. It's easier to look at the example. So what do we have now? So we have this scatter plot as before. I'm just going to put it over top. And we now have a navigation graph as before. Contains only one node. But what we now have that's of interest is this scatterplot matrix. And you notice the variates for the scatterplot matrix are these scagnostics measures. So what in this scatterplot matrix itself, every point here is a scatterplot. So we're looking at a scatterplot matrix of scatterplots. So that means we can say, what are some interesting points? Well, some interesting scatterplots might be those that we said were not convex. These ones, maybe they're also, let's see, striated. They've got lots of lines in. So we take these. So now we've got this collection of scatterplots to explore, and they all appear as nodes in this this navigation graph of things we've declared might be interesting to view. And so we can run around this and watch the structures that are revealed in the data. Wow, in the data set, you can see that. I'm just going to go back there. You see a whole bunch of groups separating there. Got all these groups with their interaction, the vertical lines and the horizontal lines. There's two groups here, another group there, and you watch them move around to kind of separate, and we could color those, identify groups. So that's definitely a way of identifying the interesting structure in the data by looking at the scatterplot matrix of scagnostics. So again, the cool features, we're looking at these more than one at a time. no matter how high the dimensionality was of this data set, we've reduced it to exploring only 9 dimensions. That's because we're looking at the pairs of variates themselves. Okay. So we could add the serial axis. I don't think I'm going to explore that there. The other thing is that having identified some structure, we might want to actually zoom in on subsets of that structure and see what's going on. So in addition to the scagnostics itself, in Loon there's the scagnostics 2D function, which returns a closure. These are closures, so they're functions that can be used to recalculate the scagnostics as need be. And when we execute this, you'll see we're going to get a scatterplot matrix as before. So scags 2D, and I'll just keep the stars there. So there's our scatterplot matrix. The scatterplots, here's the plot that it's linked to that, and the navigation graph on the left that's linked to that. So what's an interesting feature about this is the interactivity of the scatterplot matrix, so it can be updated. So let me just find the, let's go back again with the non-convex. So let's explore this. Can we find any structure? And yes, there's a structure immediately. So I may want to take this group and say, let's cut that out of the way for a moment and let's look at the remaining group. So I'll select that, I'll deactivate it. So now we have this, and I could continue now moving on this graph to see what's there, or I could ask this to recalculate itself based only on the active points. So now I have the scagnostics that are just based on this cloud alone. And so I might look at what are the clumpy ones. Wow, look at that. So now I see those separation points. I've got a navigation graph. You can see at least part of that's a single cluster. Other parts may be vertical clusters. You might use the glyphs to tell them apart. These might be clusters themselves. They might separate. That looks like a cluster. That looks like a cluster. So it's easy to start seeing this kind of structure. And that those clusters may become more apparent as we explore the space, which again, you see most of it, a lot of that space is the one variable, icoscenic. So we're going to, let me just start again. Let's just see. Yeah, so you see that separation. And now we're going to switch to this. Now we're stuck there. And why that's there is because there's all that linear structure that appears there. So that's not that interesting. So let's just look at the ones that are clumpy. But just get these back in the shaper. So the clumpy ones, scale this to the world. But not, so these are striated, so maybe I don't want the striated ones. Clumpy. Yeah, that's not striated that large. So let's take that one. I can select these one at a time if I want. See, again, I got high striated, so that one I want. And maybe some other non-convex ones, perhaps. Okay, so that gives us a more interesting data set to look at. Oh yeah. Again, the 4D version of that for the other ones. See how these non-rigid transformations, whether those groups are traveling together or not. Okay. All right, so there you have it. Lots we can do with these things. We can actually, there's nothing peculiar about those particular scagnostics measures. You could, in fact, invent your own. So we could have all kinds of measures, for example, different correlations. There's a correlation function in R. You just take the absolute value of the correlation with 3 different methods. Pearson, that's a traditional one. Spearman, that's correlation on the ranks. And Kendall's tau, or Kendall's correlation, which is another measure. Or I can invent my own. So this is best low S. I'm going to get the low S, the smooth of y on x. I'm going to see how well that's fitting in terms of how well the fitted values are, what squared the sum of the fitted values, the sum of the squares of the original, and then do the same thing on x and y, and then take the max on it. I mentioned this before, so we could use that and call that a measure. Alternatively, there's this thing, principal curve, which is kind of like a smooth. It's trying to find a smooth curve through the data, but rather than specifying one value as the response and the other explanatory variate, minimizing the vertical least squares, the sum of squares, we minimize the orthogonal distances between the points in the curve. It's a little bit more, there's no prejudice here in looking at which variate is response or explanatory. So I can do that. I can call my measures, just calling measures 2D, and I give it all of this these functions, the data that I'm going to work with, and the functions that I'm going to use, which I can name any way I want, and then hand those measures off to LNG plots, the same as before. Okay, so let's just try that to show that you can have any measures that you like. So here's our correlation measures at best low S, our principal curve, and then we'll put that inside of this LNG plot. So I now have a scatter plot matrix where instead of those scagnostics, I've got my own scagnostics that I think are of interest. So again, the scatter plot matrix allows us to choose scatter plots. And here's the pair that's highlighted. These are all the guys that have large correlation, the largest correlation available. These are the ones that have largest Spearman and largest Pearson correlation. They also have the largest Kendall correlation. And we might look at the ones that have the highest value of the low S or the highest value of the principal curve. So there's a value there. So we can look through that data set there. Let me just give you a little bit of misleading there because I deactivated some of those points. So that's what we're looking at. And these are the few that have, sorry. These are the few that have the largest value of the principal curve measure. So again, exploring through that, these measures work like any measure, any scagnostic. So the point of the illustration is just show that you can come up with anything that you like, and we can explore it, add it, and use these tools to look for that kind of structure. So you get to define what's interesting. As long as you write a function that will allow us to calculate that, we can set that up in a closure and have it recalculate on the active points or the selected points, etc. So those are scagnostics, and one way of choosing interesting pairs of variate. As I said before, we could also look at various things called projection pursuit indices, but we're not going to look at those in this course because we're primarily interested in subsets of variates, pairs of variates at the time. But you can invent your own.